Okay, what I want to do here is I want to go over some of the properties of Laplace transforms that we did not have time to go over in class. I've actually taken these slides from another textbook, but the information is nearly identical to what is in your textbook. So in the previous lecture, we talked about how to integrate to find a Laplace transform, and then we began talking about how to use formulas in the table to find the transform. There are also several properties of transforms that are important. And what this allows you to do is it allows you to take some shortcuts and use the tables when you might not ordinarily be able to do so. So the first one, which is kind of obvious because remember the Laplace transform is basically an integral. And so as a general rule, properties that apply to integration are also going to apply to the Laplace transform. What we have here is we have the property of linearity. So what linearity says is if we have some function f1 and another function f2, that if we have some linear sum of these, so a1 and a2 are just constants, and then f1 and f2 are functions that are added together, that basically the sum of the transforms is the transform of the sum. So we can transform f1 and get its transform. We can transform f2 and get its transform. The constants a1 and a2 remain the same. And so this is basically the property of linearity or superposition. The next property that we talked about a little bit on the in the previous lecture is we did talk about the time shift property. So I've just repeated that up here. So here is the transform of a function that's shifted by some constant a. And then remember, when we take a Laplace transform, we're always implying that there's a step function there that initiates the problem or the physical situation. In order to use the time shift property, both the function itself and the step function need to have the same time shift. So if that's the case, then you end up with whatever the transform of the function would have been had it not been time shifted. So this f of s is the transform of f of t multiplied by e to the minus as, which is the consequence of the time shift. Kind of an analogous property to this is the frequency shift. So if we have some function of time, and that's multiplied by e to the minus at, then basically this is just a little proof here showing what happens when you plug that into the integral. And so what happens, oops, sorry about that. So what happens is if you have multiplication by e to the minus at, when you take the transform instead of an s, you're going to get an s plus a. So the way you do that is you ignore this and you look at your function of time and you take its transform. And then once you have the transform, everywhere you have an s, you just replace it with an s plus a. Time differentiation is another important property of the Laplace transform. And basically what we have here is what happens if you have, instead of a function f of t, if you have the derivative. And this is super important because this allows us to use Laplace transform techniques to solve differential equations. So in this particular example, it's just illustrated for the first derivative. So if we were to plug df dt into this integral, the way to solve this is to integrate by parts, letting u be e to the minus st and dv be df dt dt. And then you can remember your formula for integration by parts and plug that in. So what you basically have after it's all said and done is if you have the derivative, the first derivative of a function of time, that if you take that function of time and take its Fourier transform f of s, you multiply that by s and you subtract off the initial condition. So that can be generalized to an nth order derivative, and basically it's just going to be a sum. And remember, when you have a differential equation, for every order of derivative, you need an initial condition. So if you have an nth order derivative, you're going to have nth order initial conditions. And then these s's, that's your transform variable, and it's raised to the highest power is equal to the order of derivative. And so then that multiplies your transform function, and then everything else is lower powers of s times your boundary conditions. Integration has the opposite effect, that basically if you have the integral of f of t from 0 to t, and let me point out that it is important that the lower limit of integration be 0, because remember the Laplace transform is a one-sided or single-sided transform. So if you have an integral of a function, then basically integration is equivalent to multiplication by 1 over s, or division by s. So differentiation, if you have 0 initial conditions, differentiation in the time domain translates to multiplication in the frequency domain. And integration in the time domain translates to division in the frequency domain by s. The reason this is so important is it allows us to solve differential equations by transforming them into the Laplace domain and making them into algebraic equations. Okay, this sort of works the other way. Frequency differentiation. So if f of s is the Laplace transform of ft, then if we take the derivative, we find out that we generate this t. So we can basically invert that statement and give the frequency differentiation problem, saying that if we have some function f of t and it's multiplied by t, that the Laplace transform of that is basically the first derivative of f of s with respect to s times a negative sign. And this can be done repeatedly, so if you have t to a higher power, then you just take minus 1 and you raise it to the power n, and then you take the nth derivative of f of s. So this is the property of frequency differentiation, which is time multiplication in the time domain. You notice that these properties are not, unlike if you've had a class in comms and you've done some things with the Fourier transform, you know the Fourier transform goes back and forth. In the Laplace domain, it's pretty close to being a dual kind of property, meaning time and frequency can be switched. But notice that you do tend to generate these negative signs sometimes when you go, so it's not exactly, the converse of a statement is not always exactly true. Okay, this is an interesting one, and this is one that's not in your book. And I will leave the slide for you to read over. I've uploaded these slides, or I'll upload these slides as well as the video. But this is what happens if you have a function that's periodic. So first let me say this only counts when the function starts at t equals 0. And so you can't have like a negative period, you can't have negative time here. But assuming we have something that turns on and then we have a series of pulses or waveforms or whatever, we could break that down, representing each waveform as an individual function. And then because the waveforms are identical, basically this function f2 is just function f1 times the time shift of a period, and f3 is f1 times the time shift of 2 periods. And so you can do some mathematical manipulation where you write this as a series expression. And so when I get this, basically because of these repeated time shifts, I generate these exponential functions, and then I employ the fact that there's a series relationship when you have 1 plus x squared plus x cubed. Now our x is this e, so, or e to the minus ts, so this would be x, this would be x squared, this would be x cubed in this formula. So because of that, we can basically then write it as we can write that series expression as 1 over 1 minus x, which in our case would be 1 minus e to the minus ts, where t is the period. f1 is the shape of each little individual function. So in this case, it's a half sinusoid. In other cases, it might be a rectangle or a pulse train or a triangle wave. So f1 of s is the transform of the individual function that occupies a single period. T is the period, and so then f of s would be the transform of the original function f of t. Okay, two very important theorems, the initial value theorem and the final value theorem. So basically, if you're in the S domain, you actually can get information, limited information, on what the function is doing in the time domain without taking the inverse transform. Specifically, you can get initial and final values. Now let me point out that the initial value is for 0 plus. So if you were, say, modeling a problem where you were looking at a capacitor voltage, then 0 minus and 0 plus are the same because the voltage across a capacitor can't change instantaneously. On the other hand, if you were looking, say, at a capacitor current, then you could solve this and you would get the current at 0 plus. That would not necessarily be the same thing at 0 minus. So you have to be a little careful on the initial value theorem to understand that initial conditions are not always continuous across 0. It depends on the physics of the problem. So basically what it says is if I have some function f of s that represents the Fourier transform or the Laplace transform of some function f of t, that I can get the initial value of that function f of t if I take s f of s in the limit where s goes to infinity. So this is just an example. Here's a function. Then if I take the Laplace transform of that function, I get this following equation. If I now use the initial value theorem, what I'm going to do is I'm going to take this equation and I'm going to multiply it by s. So notice in the numerator I have this expression. The denominator just remains unchanged. It's just been expanded. Now, when you're letting s go to infinity, it's almost impossible to do that when you have s raised to powers greater than 1. So in order to evaluate a rational function like this, where s is going to infinity, the easiest thing to do is to divide both the numerator and the denominator by the highest power of s in the expression. So that's what's done in this second line. And now the reason that's easy is because when s is in the denominator everywhere, as s goes to 0, the overall term, or as s goes to infinity, the overall term goes to 0. So everything goes to 0 except the 1s, so this is in fact 1. Now if we come back up here and look at our original function, then if we let t go to 0, I'll get 1 here and I'll get 1 here, so that's consistent. Okay, the other interesting theorem, and one that's maybe more useful, because a lot of times in Laplace, you're modeling what happens if you have some sort of time-limited event, like a switch closes or a switch opens, or you push a button on a control system, or something happens at t equals 0 that sets the problem in place. So what you'd like to know is when everything settles out, what does the final value of your system look like? So this is the final value theorem. So basically this is going to tell you what happens as your function goes to infinity. As your function goes to infinity, you take the limit of s f of s as s goes to 0. So here's an example here of that. Similar kind of function. Here's its Laplace transform. To find its final value, I take the limit of s f of s as s goes to 0. You can see as soon as that s gets plugged into the numerator, the entire function is going to go to 0. Here's another one. F is sine of t. So if I now take the limit of s f of s as s goes to 0, I also get 0. So basically the final value theorem can be very useful in determining if you've introduced any sort of steady state error or constant offset or something like that into your system. Okay, as a summary, here are some tables of Laplace transform pairs as well as properties of the Laplace transform. Now in your textbook, the properties of the Laplace transform he refers to as operational transforms, but it's basically the same thing. This particular book gives you these two formulas where you have the phase shift, and it also gives you this t to the n, e to the minus at, which I think is useful, but I'm not sure is in your book. Here is the time periodicity. That's another one that's not in your book. Here's the initial value theorem, the final value theorem. We're not going to discuss convolution in this class as far as going over how to do it, but another really useful reason to work in the Laplace domain is in the time domain. If you have different, say, filters or different systems that a signal is passed through, what happens is it's not a direct multiplicative effect. And so what it basically is, it's a convolution kind of effect. So for example, if you are looking, sometimes it's easier to think in terms of optics. If you're looking through a blurry lens and you're looking through a red lens and you look through both of them, what you see is kind of a convolution of blur and red. In the Laplace domain, the effects of the two systems or the two sections of the system or the two filters or whatever you're modeling are multiplicative. So convolution in the time domain is multiplication in the Laplace domain. So just some of the important ones, differentiation and integration in time are extremely important because they allow us to change differential equations into algebraic equations. Convolution in some fields, not necessarily in our class, but in some fields is very important because it allows you to work with multiplication instead of the convolution integral. And then these are your common Laplace transform pairs. So I'm going to shut the lecture down here because, well, let me just do this one illustration. This particular problem, example problem, illustrates the property of linearity. So you can see we have this sum, and we're told that this function is valid for t greater than or equal to 0. So basically, by the linearity property, that's just each term is separately, the Laplace transform is taken separately for each term. So you can see what happens when you get a common denominator is you have this expression. Now, the reason I want to go over this problem is let's suppose we were given the function in the S domain and we were told to take the inverse transform. Okay, we could look up on the table and we could see that the inverse transform of 1 is the impulse function. The inverse transform of 1 over S is the step function. And the inverse transform of 1 over S plus 2 is e to the minus 2t times u of t. However, if we look at this in its simplified version, and we were to have to do that, that would be impossible to know. So when taking the inverse transform, this is just kind of a heads up, when taking the inverse transform, what we have to be able to do is we have to be able to get this functional form, and we have to get back to this form where each term is something we can look up on the table. So as we move from Laplace transforms to inverse transforms, that's part of what we'll be learning how to do.